All right, welcome back to the drinking water and the water treatment section of VHS 300. In this video, we're going to focus specifically on the water treatment process, the drinking water treatment process. So you'll also have a video, if you haven't already watched it, of Barry's drinking water plant tour of a water plant in Canada, where there's a lot of similarities, but their disinfection steps are a little different. We disinfect with chlorine. They use ozone in their video. But we'll go through this process from intake to chemical addition, coagulation and flocculation, sedimentation, filtration, disinfection, water storage, and water distribution. This is another example. Water comes in from a reservoir, chemical additions, the addition of a coagulant, the mixing and the slowdown of the mixing, sedimentation, filtration, disinfection, water storage, and then it goes to the distribution to the houses or businesses or industries. Here it also shows the sludge being collected. And the sludge here, it has it being hauled off. But sometimes it's just land applied. Here it doesn't show the sludge collection. So, first steps. We'll focus on the Richmond water plant for now. Water intake. So intake has to come from somewhere. You should know or remember, if you're getting it from a lake, you don't want to be drawing from the top or from the middle. You want to be drawing from the upper part of that hypolimnion so you don't have any plant life. But sometimes you have to draw from shallower water if that's all you've got. You also want to have intake screens to prevent fish or logs or sticks from getting in there, so these big metal grates. Then we're going to do clarification. We're going to clear the water up, and then we'll do disinfection with our clear water. We don't want to waste disinfectant or add unnecessary amounts of disinfection byproducts by hitting it with too much chlorine early on. So intake. So at the Richmond water plant, on the Kentucky River, even on a muddy day, they draw water. Even on the muddy days, it actually cleans up better because it kind of settles like a big blanket in their water plant. The screens can periodically get clogged. They have a big air compressor that they can shut the water off, reverse this, and throw a big blast of air, and it looks like a depth charge going off in the river. So they can clean the things off when they need to. They have these huge, massive Mitsubishi pumps down there that pump this water up that big hill from down the river up the big hill to the water plant. Some lakes and places have these towers, so that is a big giant straw that suck the water up and send it to the water plant. They have those screens on them because we want to keep fish and woody debris and algal mats and stuff out of the water. If we have a lot of sunlight hitting nutrient-rich waters, algal slimes and biofilms and all that can clog up those screens. Also, invasive snails and invasive mussels like zebra mussels, which pretty much act like a glue, can clog up the screen. So you can see this shopping cart that was in a zebra mussel contaminated lake. So zebra mussels are not native to the United States, but they're becoming endemic in many of our waters, and not just endemic, but they take over. And they're a big problem for drinking water intake screens. We definitely want to screen them out if we can. After we have pulled in the water, we will then do coagulation. Coagulation is a step whereby we add the chemicals, a coagulant, and it produces these larger things called flocks. So you add the chemical, and it produces flocks, which are these little round globs of usually mostly sediment that are able to be heavy enough and they stick together enough that they then settle out when we slow the water down. Before we do sedimentation, we have to do coagulation. Coagulation is the enhancement of collisions between coagulants and particles. This process is accomplished by large stirring of often paddles or agitators in what's called the flash basin or flash mix of a water plant. Coagulation itself is just the addition of the chemicals, and it's this mixing process. So the rapid mixing process is the coagulation, the addition of the chemicals and the mixing. This is different than flocculation, which is related. Flocculation is when we slow it down and start seeing the flock appear. So coagulation is the addition of the chemicals for the purpose to make flocks and to do flocculation. Coagulation is the addition of the chemicals in the fast mixing process. Flocculation, we slow it down. We've stopped mixing it and we've slowed it down, and the particles known as flock start to form. Some water plants have they all have this, a bunch of jars, little paddle wheels inside them, where they can add different chemicals to optimize their process. The optimization is which set of chemicals will make the most amount of flock with the least amount of chemical. You want to be efficient in your process. At the Richmond water plant, after the chemicals are added and flocculation starts, you will actually see these little beads form in this water. You can look at them and see them. These little, not bubbles, but these little round globs. So it'll be turbid or muddy water, but the water, beyond it being just turbid or muddy, you'll see the even bigger little chunks of things sinking. Coagulation is that process of adding the chemicals and doing the mixing. Coagulation can be enhanced with warmer temperatures, higher pH levels, and higher alkalinity values. Aluminum sulfate, or alum, was the original coagulant that was used for decades in the United States, and it's still used all around the world and at many water plants in America. It does require a lot more alum to produce the amount of sediment and to produce the amount of flocks if you're choosing to use alum over aluminum polyvinyl or these other polymer products that are out there. Yes, the other products cost more per pound or per ton, but you don't need to use nearly the amount and you don't generate nearly the amount of sludge. Aluminum sulfate produces a lot of sludge just by its own weight alone. So things that are like this, though, aluminum has a lot of positive charges associated with it. So you think of like the aluminum compound as Al3+. So that positive charge on aluminum gives it some ability to be a pretty good agent. Aluminum also is not linked to a lot of adverse health effects. It's pretty good with humans. So that's another reason why it is used. Again, higher pH levels make this stuff work better. So what chemical would raise the pH and raise the alkalinity? And the chemical that people use as an antacid when they feel like their stomach's got too much acidity is what? They use Tums. What is Tums? Calcium carbonate or limestone. So some water plants in parts of the United States with acidic or low pH water will add lime to make this process even better. If you're having to add a lot of lime, you are again increasing the amount of sludge that your water plant's going to have to deal with. But ultimately, the goal of coagulation is to produce a lot of flocks to facilitate sedimentation. So coagulation, we've added the chemicals and fast mixed them in. Flocculation, we've started to slow the water down so that we have flocks form. And now we're at sedimentation. And sedimentation, we spread the water out over a larger area and slow it down even more. And this is the time where the flock actually starts to hit the bottom. It legitimately settles out. This is the settling period in the water treatment process in which mixing and flow are minimal for the facilitation of the settling of solids. Some of these are rectangular, some of these are circular. Often at the bottom, there is some wheel or an arm that goes around the bottom that scrapes the sludge. Some water plants have a moving bridge with a giant squeegee that's pushing it all to one end. Some have a vacuum. Some have a Roomba-like vacuum that goes along the bottom and sucks it up. They suck the sludge, which is the sediment, off the bottom and send the sludge to sludge drying beds. So here it talks about a sludge scraper arm that pushes it all to one side and then it sucks it out of there. The sludge comes out in a wet or gelatinous type form. You can think of a bunch of like wet, soupy mud. That mud has to be dried out so that it can either be hauled off or land applied. At the Richmond water plant, the sedimentation process looks like this. You can see the flock moving from this direction, and then boom, all of a sudden it all settles out. So now this water is a lot more clear over here. Sedimentation basins are sometimes larger than or not larger sometimes, but almost always larger than the flocculation basins that exist. Some plants have baffles. Other plants have what are called tube settlers, where the water kind of rolls across a bunch of little pipes that make it kind of ripple at the bottom, and that causes the sediment to more easily fall out and be sucked away. Again, there are systems that are rectangular. There are systems that are circular. Ultimately, the sludge still gets collected. The goal in this process is clarification. We're trying to clarify or clear the water up. We're clarifying it. Once we have removed the vast majority of the sediment from the water and the vast majority of the turbidity from the water, approximately 5% of suspended impurities still remain in the water. Therefore, we have to remove that as well, and that's when we use filtration. Filtration is the movement of the water through porous material so that we can remove suspended particles. So we're removing suspended particles by pushing the water or passing the water through a layer of porous material, like sand. There are a variety of things that are used to make this porous material work. Some places just use giant sand filters. Some use sand, coal, garnet, and gravel, or a mixture of all of these. The Richmond water plant has these rectangular banks or basins inside. You can see Lonnie Banks there discussing these filter basins that are back there. And inside of each one, below the water, is anthracite or coal, fine sand, a little more coarse sand, all the way down to some gravel, and then to some larger gravel. And the water sits on top of all this, and by the weight of the water, pushes down through all this material, and at the bottom of it, the clean water comes out. They have instruments that are in here that are constantly measuring the turbidity of the water leaving this. These instruments also measure how high the water has to be in terms of head, or the feet of head, the amount of weight the water has on top of this that has to push down through here to make this process work. If the head pressure gets too high, meaning that there's way more water that has to pile up on top of that, when that weight or that height gets so high on top of that filter to push water through it, when it gets so high, they know that the filter is starting to clog up or lose its effectiveness. So they will turn a switch and turn off that filter, and then turn another switch to backwash, where they will push water up through it and boil the water off essentially through the back pressure, take that water out and send that water back to the river. That water has to be permitted. They have to pay attention to it. And it's coming from the river, but it does have aluminum in it at that point. Not much. And that backwash water, though, is something that you need to get rid of because you don't want to reuse it. It's going to have a lot of mud in it. But that backwash process is how you clean those filters. And when they're done doing that and they switch it back onto a back to the normal operation, before they start activating the water again for the water treatment process, they let it run a while, and that filter will actually normalize back to these same layers based on the specific gravity of the materials that are in there. And they've got about 16 of these filters running at that water plant. They first started off with like 8 a long time ago, and then they expanded the operation maybe a decade or so ago, or 15 years ago, and they have a lot of extra capacity to service the Richmond community as it needs to grow, and they can use more filters as needed. There are other filtering options that are out there. There is slow sand filtration, which is much slower than rapid filtration. It's effective, it's less energy intensive, they're more economical, but you need a lot of area. So here's an image of a slow sand filter at a treatment plant in Ohio. You need a lot of flat ground. This area for slow sand filtration is larger than the whole water plant. This one is recently offline. This one is ready to be used, and these are actively being used. Water in slow sand filtration is being sent from the sedimentation basin to the slow sand filter, and over time the water will work its way through the sand and go to an underground storage well, where it'll then be ready for disinfection. After a while, they will want to switch to a new drying bed or sand bed so that they can collect or scrape this stuff off. This stuff is easier to scrape off, the old sludge. It's easier to remove when it's dry. When you don't let it dry, or when you let it get too thick and deep, it takes a very long time to dry, and it's very heavy to scrape off and hard to remove. So you don't want to run these too long, and you want to monitor how much sludge is collecting. Experience goes a long way with your water plant and knowing how long to let these run. And it's always good to have a backup one ready to go. All right, so that is all on the filtration for now. I want to let you know that the rapid method is more expensive and more energy intensive, but requires less labor. And as labor costs go up, the expensive part may not be as much expensive. You can also generate water more quickly. So you may want to use these if you've got a large community, and you need more land area to do that. So if you don't have the land area or a lot of flat land, you need to do rapid filtration like they do at the Richmond water plant. The next set of videos are going to focus on drinking water disinfection. And there are several disinfection options that are out there. Richmond uses bleach or sodium hypochlorite, but there are a variety of options out there. Your quiz will include questions related to MCLs, drinking water disinfection, health effects, which steps in the water treatment process are used to do different things, what are some reasons why water intakes may be clogged. There are other review slides, what chemicals are used for coagulation, what chemicals can enhance coagulation, which are different than chemicals that are used for disinfection that we'll talk about later. And then what's the name of that test that was used for determining the optimal coagulation? We saw the different beakers. What types of media are out there for doing filtration? What types of disinfection are used in the drinking water process? Are total coliforms ever permitted in treated water? What about fecal coliforms or E. coli? And then there's going to be a video that you're going to watch on the largest waterborne disease outbreak in at least U.S. history. And did it come from humans or animals? What was the pathogen? And what probably caused it? So that's all for this video, and I'm going to stop it right here. Again, if you have any questions, feel free to email me at jason.marion@eku.edu, and hopefully this has been helpful, and I'll stop it there.